This was the number 4. For you also?
Oh, I don't remember.
Took a picture?
Of my test, no. I forgot. Most of it.
I know. Then I see.
I know the test lessons. I know.
Not all. You need to be lucky which if you are
It took me a different test next time, that's why.
because the last two I checked were not similar. Because only one guy who had no
One plus Hey, you want?
No, thank you.
She doesn't.
Ready to think about mathematics, or ready to go to the cafeteria and have some coffee and chat? I have no problem with that. I would gladly have some coffee and relax. Okay. Functions of two variables. Of course, we can do the same with functions in 3 and more variables, but for functions of two variables, we are going to discuss composite functions. The partial derivatives of composite functions of several variables. The thing is that 2 days ago you might say that 2 days ago we already considered some composite functions. The thing is, those composite functions depended on just 2 variables, and they were composite in the sense that there were different functions written, composed, if you like, together. When we talk about composite functions in terms of functions of several variables, we basically mean that the original function depends on 2 variables, and then those 2 variables themselves might depend on something. Of course, the difference in principle is not very great, because basically we can rewrite any composite function that seems to be depending on more than 2 variables into the type we saw 2 days ago, or we can find the function depending on 2 variables and being composite. We can actually construct some structure and observe some structure. But the point of these partial derivatives that we are going to discuss today is to make differentiation easier, simpler. Otherwise, it might simply become extremely complicated. So let's imagine that we have a function where z depends on some variables, let's say u and v, some function z, which depends on the variables u and v. And we have several possibilities, several situations. So the worst possible case where the function of 2 variables is a composite function, it actually happens if each of these 2 variables, u and v both, depends on two other variables. In other words, if we have the function z depending on variables u, v, and then each of these two variables depends on two other variables, x and y, for example. So u is u depending on x and y, and v depends on x and y. Then we have an interesting composite function. And the thing is that many people, when they see something like this, many people feel tempted to express u in terms of x and y, express v in terms of x and y, and then put it in there, making that expression of the original of the given function extremely complicated and extremely unpleasant, to integrate or derive. And that simply, well, it can be done, but why complicate things and why waste time for this? So basically what we can do with this, to find the partial derivative of z in terms of x, we will go through both u and v derivatives in terms of x. Which means if I want to find the derivative of z in terms of x, I will write it in two different ways. I will write it in this prime notation, and I will write it in the dz over dy dx notation. So the derivative of this function is, first of all, we derive z in terms of u, partial derivative. Then we multiply by the derivative of u in terms of x plus. Next part. We derive z in terms of v. We are going through the second variable, z in terms of v, times the v derivative in terms of x. So this already involves 4 different partial derivatives. Even so, these partial derivatives, using partial derivatives 4, well actually we'll have 6 of them, separately, is easier than putting everything into the same pot, a huge function, clumsy function expressed in terms of x, y, and then attempt to find the derivative. That will be a lot more difficult, and I strongly advise you to avoid that situation because it complicates things for you. And yes, of course, for me, if I have to read it and try to understand what you meant, but still. And what happens when we need to find the derivative, partial derivative by y? We do the same thing, we go through the derivatives of u and v, but at this time we will use the derivative by y. So it will be z derivative by u, so alright, it's the same, times u derivative by y plus z derivative by v times v derivative by y. So we see that we have 6 different partial derivatives, z by u, z by v, repeated here, u by x, u by y, v by x, v by y. In other words, we derive each of these functions twice, obviously, to find the partial derivatives by both variables. So we have 6 different partial derivatives. And the trick is, of course, to remember how to put them together to obtain the correct partial derivatives of the original function that we need. Basically, it is quite simple because generally those functions are not extremely complicated. The resulting function would be extremely complicated, but if we split it into little bits like u and v, then it becomes actually quite simple. And I might have a look at a specific example. For instance, I'll do the example in blue for the sake of change. The example, let's suppose that we have the function z of u and v written as square root of u times natural logarithm of v squared plus 1. And then we have u in terms of x and y written as 4x plus y squared, and then we have the v function also in terms of x and y, which will be, let's say, x minus 1 divided by y squared, like this. Now, if I take this and try to put it in there, believe me, it's not going to be pleasant. It's going to be rather messy. So I am not taking these and not putting them into the original function, because finding the derivative of this huge composite function will be complicated, messy. It's very easy to forget one step, to forget the chain rule at some point, to forget to use the chain rule at some point, so perhaps better not. So perhaps it would be better to find all 6 derivatives that we need, and then simply put them together, await the final answer. So the z partial derivative by u. This is a constant for u. So it seems that we have constant times square root of u. The derivative of square root is 1 divided by 2 such square roots. So, alright, the square root of u divided will be division by, 2 square roots of u. And of course this plays the role of the constant in this case. But it is possible to have more complicated functions, of course. In this case it's quite easy and not so bad, because that makes our task easier. Z derivative by v. Now, this is the constant, and we simply leave it there because it's a constant. Derived natural logarithm. Now, this is also a composite function, but not a very bad composite function. The derivative of logarithm is 1 divided by v squared plus 1. And we need to apply chain rule to derive the inner function by v, that will be 2v times 2v, like this. So we have 2 derivatives which were comparatively simple to find. It would be much more difficult if I had to put those functions in there and do something more with these. Now, next, the derivatives of u derivative by x and u derivative by y. U derivative by x is simply 4. We are lucky, the function is simple. U derivative by y, 2y. V derivative by x, v derivative by y. V derivative by x, what do you think?
Just 1
over y squared. Because if we separate this into 2 parts, into 2 fractions, x over y squared minus 1 over y squared. 1 over y squared is a constant with respect to x, so we only need to derive x over y squared, where 1 over y squared is a constant again. And the derivative by y, so we have the constant x minus 1 multiplied by y to the power minus 2. If we derive that, we multiply by minus 2, so minus 2 becomes a factor, and the exponent becomes minus 3. So I divide by y cubed. And now, fairly simple derivatives, fairly easy to do. All I have to do is write the answer to combine all 6 derivatives to produce this. So z derivative by x would be z derivative by u, that's ln of v squared plus 1 over 2 square roots of u, times u derivative by x, times 4, plus z derivative by v, which is square root of u plus 2, times 2v, times 2v divided by v squared plus 1 multiplied by v derivative by x means times 1 over y squared. If possible, they can be simplified a little bit. For example, 4 and 2 could be cancelled out a little bit and so on. But basically, the one mistake people make, basically wasting a lot of time that could be saved for better things, trying now to put V and U into this. Absolutely no need. This is perfectly acceptable, even though at worst it contains 4 different variables, U and V and X and Y. At the moment, we don't need to do anything else. So if necessary for practical purposes or for scientific purposes, of course it is possible to take V of X and Y, U in terms of X and Y, and put them in there, if necessary. At this point, we are actually dealing with derivatives of composite functions, with looking at what has to be done, and then finally polishing up the results, making them pretty, can be left for now. So don't try to put V and U into the derivative. Don't try to put V and U into the original function and derive after. That will make things worse. It makes things more difficult. And of course, the second partial derivative by y, again, z derivative by u ln of v squared plus 1 divided by 2 square roots of u times u derivative by y, which is 2y. And yes, we can simplify it a little bit. Plus z derivative by v square root of, I will write 2v square root of u over v squared plus 1 times the derivative by y, which is this. Okay, at this point I'm just writing it like this, and if necessary, it can be simplified. It can be simplified. Basically, I would prefer to simplify personally, but okay, I'm forcing myself to stop here and not to try to do anything else. So, yes, of course, we might multiply, we might write minus 4v square root of u, x minus 1, and so on. We can bring things on the common denominator, if you like, or on 2 common denominators consisting of 2 parts. So the thing to remember is that we need 6 partial derivatives, which are all relatively simple. And then we put them together if we know how. If we remember how, or if we have made sure we understand how to put them together. And as I said, it's much easier than taking those functions, putting them in here, and then attempting to derive. It is possible, as I said, it is possible, but it's more complicated and more difficult. So why bother? So how to remember these? Of course, we start the normal chain rule. We do the normal chain rule. So normally we would of course go through the only variable and then times the function, that variable in terms of the internal variable. In this case, because we have 2 of them, we perform it this way. So the derivative by u times u derivative by x, derivative by v times v derivative by x. So we have to go through both of these variables, but because we are deriving by x, we are just putting u by x and v derivative by x here. And the same goes if we want to derive by y, the partial derivative by y. Again, we have to go through both of these, u and v, because they are combined in some kind of expression, and multiply by the corresponding derivatives by y, because we are not considering the derivative by x, since that would be 0. So this is for the worst case. This is the most complicated. This is really the worst situation possible for composite functions into 2 variables. So if you are not scared by now, then the rest is going to be technical. The next possibility is quite nice from our viewpoint. So the next possibility is better. Supposing we still have a composite function, but the variables u and v depend only on one other variable, not two other variables. So I might write if z depends on u and v, and then u depends on some x and v depends on some x. Simpler than there. Actually, I have used a slightly different notation. I have named the variables x, y, and they both depend on t, which is quite a common thing, processes depending on time. Why not? So I'm actually going to do z depending on x and y. Z depends on x and y. X is x dependent on t, for example, time. And y is dependent on t, for example, time. So I'm erasing this part now because I only wanted to show you the similarity to the previous case. In this case, though, because there's only one internal variable t, we don't need two expressions. We only have the one and only variable t, so what we do is we only have one such sum. Only one. So basically what this ends with, it ends up with z being dependent on only the variable t. So that's not even a two-variable function. But as we see, a two-variable function can be used to make derivatives simpler, if, especially if the z function is extremely complicated. So I would do z derivative. And in this case, I'm not writing the variable down there because this is not a partial derivative. This is the exact derivative, the complete derivative. Because fundamentally, z depends only on a single variable. So it's a normal function, the one we were discussing, the likes of which we were discussing last semester. So we have z derivative by x times x derivative by t plus z derivative by y times y derivative by t. That's it. This is the exact or the complete, the full derivative. These are partial because they are by one of two variables. This, in the end, has just one variable, the independent variable. So this is the exact derivative, the complete derivative. There's nothing else. So this is a simple case. So this is the simple case. The complete derivative, the exact derivative. And finally, another case, even simpler than this, the third situation. So let's suppose we have z as a function in terms of x and y again. This time, only y is dependent on something else, and that will be x. So sometimes we could have, for example, y dependent on x, and then some expression that's dependent on both x and y. In other words, a composite function which involves some expression, some function of x, and also x alone. It's also the exact derivative. Again, even simpler than this, because if I want to follow this, x derivative by x is 1. X derivative by itself is 1. So actually we have something like this. Z exact or complete or full derivative is z derivative by x times x derivative by x. It doesn't depend on anything else, but that's 1, so I don't need to multiply by anything. Plus z derivative by y times y derivative by x. So this happens when we have some function involving x as a single variable, and also some expressions using y and x. Basically, it is seemingly a function in two variables. It pretends to be a function in two variables, but basically one of these variables actually depends on the first variable. So in the end, it ends up as being a function of one variable. But again, If the functions are complicated, and yes, they do happen to be complicated in engineering, physics, and so on, then it's easier to derive them this way than to struggle with this huge multi-layer, multi-level expression. All right, so this was, I showed you the example for this situation. This is much easier, but you understand the principle. The principle is the same. So first of all, we prepare these four derivatives separately, because it's easier to do them separately, and then we put them together. If we want to simplify the expression afterwards, then yes, of course, but basically it's much easier if you do them separately. And in this one as well, we do the z function derived by x, z function derived by y, and then because we know that y depends on x, we also do the y derivative and put them together in the same way. So this is actually very similar to this, only we could say, okay, if x is x, x depends on itself, then it's multiplied by 1. This becomes 1. No problem with that. So we started with the worst case and moved on to simpler cases. Now the exact differential. If we remember, well, I do remember what the differential of a function was. We started this semester with the differential of a function. In order to be able to integrate, we needed to understand the differential of a function, if you remember. For the old functions, again, so what I'm trying to do is, I am reminding you of the connections and patterns and ideas from the previous calculus in one variable, and trying to show you how this applies to two variables, or sometimes three variables, or four. The number then doesn't matter. So remember that we had this, dy is y derivative dx, right? That was this old thing. I had it on the board 2 months ago, a lot of times, for methods of integration. I had it. Perhaps I used u instead of y, or t, or something else, but it's still the same. We had it. So the complete differential, the differential of the normal old function in one variable, remember, it was the principal part of the increase of the function. So we said, okay, like this, we said, okay, if I move by delta x, if I move out of my specified point by dx, I see the function has changed, the change of function delta x, delta y, and then I said, or we saw that it can be approximated. If I simply look at the tangent line, I can just take the principal part of the increase of this function. I didn't take the total increase, the actual increase, but I took the principal part only until the tangent line. And that was an approximation. And we said, okay, this is a good approximation for the change of the function. So this was the dx. And that's how we actually obtained that expression, because delta x is the same as dx, but, this was dy. Here. And dy was the differential from trigonometry, from tangent of this angle. We obtained that expression, and we saw that it's only a little bit missing, from the complete increase of the function. And for very small dx or delta x values, we said, okay, we can use the differential instead of the delta, because it's almost the same thing. And now if I do it in two variables, now we have to understand that, of course, as long as I do it in one direction, I could do the same. I could derive, for example, by x and multiply by dx, by delta x. But that means that I only get the basic increase of the function going in one direction. If I have moved, so now I'm looking at the domain. I'm looking at the domain now from above. So the z values are somewhere there. But this is the xy plane. This is the xy plane. So we have this point x0, y0 in the domain, in the xy plane. And we might, for example, we might do a delta x. We might do a delta x. And we could see that the increase, the change of the function in terms of delta x when we move only in the x direction. But generally, if I'm in the plane with two coordinates, in the coordinate plane, then moving from one point to another point actually involves the change in both coordinates, usually. It involves the change in two coordinates. So it involves the change dx, and it also involves the change dy. And that's why we have to consider both of them, both these. So first of all, we might think like this, to evaluate the change of the function values between these 2 points, the old point and the new point. So in the old point, the function value is something. I step to this new point, and there the function value is something else. And I want to see the difference. I want to see the increase, the delta z. I want to see the delta z. So, all right, I think I have to erase the old stuff. By now, this is already old. So if I want to see the change between the function values, of course the function value is different here and here, I might do it like this. First of all, I evaluate the change in the x direction, see how the change is like this. And then from there, I move in the y direction and I say, oh, there's an additional change. Because I move this way, there's some change in function value. And then I change my direction and I move this way, and there's another change added to that. And that's why we have the exact differential consisting of two terms. It's a sum of two differentials, sum of two partial differentials. In other words, I can derive the function by x and then multiply by delta x. Similar to this, remember that dx was exactly delta x, exactly the same thing. So I can multiply the derivative in the direction of x by dx. So I get this part, the principal part of the increase of the function when moving in x direction only. But then I have to remember that if I move in the y direction, I get another part, another component. It moves some more. So I could write, I should add. So when I have moved to this point and I have a new function value, this is the more or less approximate change. Then from this point to this point, the function value will change again. This time, of course, is going to be in the y direction, like this. And this is how we find the exact or the full differential of a two-variable function. The full differential is denoted by dz, using the same old letter d, and it can be written as z derivative by x times dx plus z derivative by y times dy. dx and dy are these two independent small changes in coordinates. Independent small changes, because if here we had y dependent on x, this was the one variable function. Here we have x and y independent, but z depends on both of them. Or we can write it, if you prefer the dx over dy, dz over dx notation, this can be written as dz by dx. Remember that these strange d letters, Gothic d letters, mean they are used to signify just that. They are used to signify that this is a partial derivative. This is not the actual complete derivative, partial derivative, times dx, and in this case, might be the same, might not be the same. You have to be very careful because the symbol, symbolically it means something else. Symbolically it means something else. It's not the actual division, it's the symbol for the derivative. This is the symbol for the derivative. Times the change in x plus the partial derivative of z by the second variable y times dy. And this then is the exact differential of the function. Again, it is basically, geometrically, it means the principal part, the main part, the important part of the change in the function value. So, what I have found, if I do this using numbers, if I do this using numbers, what I have found is the answer to the question, if I move from this point to this point, how much does the function value change? This is only an approximation, of course. If dx and dy, if these are small, so dx again was renamed, delta x was renamed dx, delta y was renamed dy for the sake of symmetry in this case. So it's not the same as here, not exactly. So I'm now erasing the old part, the single variable function. We are thinking now that x and y are independent variables, both independent. So we rename this simply to keep to the symmetrical notation, although you may leave delta x and delta y there, no problem. You may leave delta x, delta y, it is the same. Delta x is the same as dx and delta y is the same as dy here. But this is something else again. So dz is the principal part of that change. Obviously it is the distance, from the first function value to the tangent plane of the surface. Obviously the tangent plane doesn't lie too closely to the surface. There is some gap between the tangent plane and the surface. There is some gap close to the tangent point. So that gap is the difference between the differential and the actual increase of the function. But as previously, it is the differential of a function, the exact differential of a two-variable function, is the principal part, the main part of the increase of that function. It can be used as an approximation. And practical applications, of course, could be used for some expressions, some equations to be solved. What else is left from theory here? General theory. We had things like second derivatives or derivatives of higher orders for single variable functions. In the same way, we can have higher order partial derivatives of two variable functions. So, again, if we think about the single variable function, if we had y is a function of x, then we could do the first derivative, and then we could do the second derivative, which was the derivative of the first derivative, and so on. We could derive it several times. Remember that the second derivative meant the curvature, concavity up or concavity down. It was used to analyze inflection points. Here, the second derivatives can also be used to find concavity up or down or no concavity at all, minimum maximum points. We can have z derivative by x derived a second time by x, and then we say it is the second order partial derivative both times by x, derived by x and then derive that derivative by x again. That's a second order partial derivative, just like we could do it with single variable functions. We could take the first derivative by y and derive it again by y, and then we would have the second order partial derivative by y and by y again. But then we could take the first derivative by x, derive it again by y. So we have a second order partial derivative by x and then by y. And we could have the derivative of y derived by x, so that would be the second order partial derivative by y and then by x. If we are very lucky, and you are going to be lucky indeed, if the function is continuous at that point, these two derivatives should be identical. If they are not identical, then the function is not continuous at that point. There's something, or the function is behaving strangely. If the surface is continuous and smooth, then these two derivatives should be the same. They should be identical. Derived first by x and then the second time by y, or derived first by y and then by x. So these two derivatives are usually for nice functions, they are the same. Now and in a similar way, we can find the second order exact differential when we find the derivative of this, and then we construct the second order partial derivative. It is possible to do. We are not going to investigate any applications, but generally the second order partial derivative will look like d2 of z will look like the second partial derivative by x multiplied by dx squared plus 2 second order derivatives by the mixed derivatives, partial derivatives that are mixed by mixed variables, of times dx dz plus second order derivative, partial derivative by y, both times multiplied by dy squared.
And dz or dy?
Sorry, dy, yeah, thank you. dy. So this happens if we try to find the derivative of this. So the second order differential means we take the first order differential, derive it, and apply the same situation. When we derive it by x, we multiply by dx. When we derive it by y, we multiply it by dy. This can be actually tried. So you take this, derive it again, and see, constructing the second order partial exact differential of this. We take the first order differential, we derive it by x, and multiply by dx again. We differentiate it by y and multiply by dy again, and then simplify. It's very simple actually. You can get this in the end. But this is something that not too many of you might need. Very few people will need this.
But what is dx squared?
Dx squared is dx squared times dx, just that. If I put a 2 after d, it means second order derivative, because it's simply an operation performed again. But if I put a square after dx, it means a normal square. So here, the 2 means operation performed twice upon the result of the previous operations. But here, it means simply a square. Let's have a look at some application of the exact differential. Again, for practical purposes, I know you have computers, there are technologies that will do everything, but if somebody wants to somebody wants to do computer technology or programming or engineering, then you have to understand what's going on so that you can use the correct applications for your computer. Okay. So we will consider basically one application, and that will be how we can estimate, for example, some unpleasant expressions like 1.03 taken to the power 2.07. So how can we evaluate this? How can we evaluate this? Yes, I know you can put it into the computer or calculator as well. Okay? That's, of course, that's normal. But let's see, well, it will be interesting to see how that computer is doing it anyway, because it will not be the exact value. What's going to happen here is we are thinking of this in terms of a function. Z is x to the power y. Let's think about the function. Z is x to the power y. I'm just looking at the form of this expression. I'm constructing, building a function. I have to choose x and y values close to these, but such that it's easy to perform this function. Obviously, let's say if x0 is 1 and y0 is 2, then the function value at this point, 1, 2, is 1 to the power 2, it's 1. So that would be the starting point. For finding the differential, it's the starting point. For example, I know that if x is 1, y is 2, the function value is 1, a fixed point. I know. And now, I would like to use the exact differential to find the change in the function value. And then I will add the change to 1, and I will know the approximate value at that second point. So for this, obviously, we will need dx or delta x. Dx or delta x is obviously 0.3 because I need to step 0.03 in the x direction. I need to step 0.07 in the y direction. I'm trying to get material to put into this formula, this or this or this, whichever shape you want it, it's the same. So, all right, I have delta x, I have delta y already, bless you.
Sorry, what's the equation for delta x?
0.03. I'm taking it from the function. I see the change from 1 is 0.03. I'm taking it from the original function. Now I need the value of the partial derivatives. The values of these partial derivatives. So this means, first of all, I need to find the partial derivative. So z derivative by x. Z derivative by x is y times x to the power y minus 1. We all know that. Should know that. Z derivative by y. Now we have an exponential function. It will be x to the power y times ln of x. We had this 2 days ago. Exactly this. We had this 2 days ago. So I'm not going into details of how to find this. Should be clear. Or at least you could flip back a couple of pages and verify. Okay, so now I still need numbers because I need the numerical value for the differential, which means I need to put x and y values in here to get the final value. Of course, what x and y values are there? These. The original x and y values. So I'm putting the values of 1 and 2 in here, so I write 2 times 1 to the power 2 minus 1, which is 2 times 1, that's 2. And then I take this one, 1 to the power 2 times ln of 1. Natural logarithm of 1. 0. And now I take the formula of the exact differential and put these numbers in. So my dz, the exact differential, is z derivative by x, which is 2, times delta x, which is 0.03, plus the derivative by y, which is in this case 0, times the delta y, which is 0.07. I'm writing out the complete expression. Yes, I know I could skip this, because as soon as I see that it's going to be 0, I could just stop there. But I want to write down the complete expression, because in other exercises, in other questions, in other situations with other functions, it might be something different. So now I see that this is 0.06. It is the exact differential at the point 1, 2 for the change of x 0.03, change of y 0.07. This is an approximation of the differential of that function. So I have to say that this is approximately delta z. It's approximately delta z. It is dz, the differential. It's approximately the increase of this function. So now, obviously, this should be the basic value. The basic value, it's this, 1, plus, obviously, well, dz, the differential, the approximate increase. So this is 1.06. If you have a calculator handy, you might check. You could try to check. So 1.03 to the power 2.07. Just see how different from this it is. All you have to do is punch some numbers into your phone calculator.
1.06309.
Okay, not so bad. 1.0630 and so on. So the relative error is very, very small actually. The relative error is very small. So it's quite good. Two decimal digits or 3 significant figures, that's fine. That's a good approximation. All right. We still have some 25 minutes to practice and look at some exercises. Leave some of these here.
It's an approximation.
So, one of each and one.
Try this.
Another one of each. Okay. One. Okay, I'll just take some. So 1 and 1. Take 1 and so there are 2 sheets. There are 2 sheets. So 3 pages.
This page. jetzt alle das gegenüber. Und dafür ist es only one.
Is there something wrong? There's something wrong. So many people there.
Like 96.
I want to do it something here, but my brain is
Everybody have two papers. Everybody has that, yeah? Okay. Yes. Yes, because if you can understand forms, then you can understand the symbols. That's good. Get extra hands. All right. Starting with the unpleasant one, 1919. So the U, I don't remember which time, which side. Okay, U is natural logarithm of x divided by, oh no, sine, I forgot the sine. Sine x over square root of y. X is 3t squared and y is square root of t squared plus 1. In this case, we can see that this is the second type of composite. The original u function is in terms of two variables, x and y. But x and y each depends on only one variable, e. So this will be the simple situation with the exact derivative. So I will have the u derivative by t, u derivative by x times x derivative by t, plus u derivative by y times y derivative by t. So the thing is, nice music. So you have to remember that to get to the derivative of composite functions, you have to think about chain rule. It's always chain rule, and then of course it's always the same variable through which we are going. If we start deriving by x, then x derivative is the next multiplied by it. Alright, but we need 4 derivatives for that. U derivative by x. Okay. Natural logarithm derived is 1 over whatever is in there. 1 over sine x over square root of y times chain rule. Chain rule. We still haven't reached the end of this. Times the derivative of sine, which is cosine of the same. Finally, times the derivative of this inner function, and now we have to think. We are deriving by x. So the y is a constant, so that will be 1 over square root of y. That's the derivative of x over square root of y in terms by x, in terms of x. So 1 over square root of y is just a constant. I could simplify this, of course. I could simplify this. I could write it as cotangent of x over square root of y times 1 over square root of y. U derivative by y, the first part is the same, natural logarithm is derived still in the same way, 1 over sine x over square root of y times sine, derived in the same way, nothing has changed, times. Now, because we are deriving by y and not by x, the derivative of this internal function will be different. So it's x times y to the power minus 1/2, and we are deriving by y. When we derive, we multiply by the exponent, so it's minus half, and subtract 1 from this exponent, so this will become minus 1.5. In other words, it will have u to the power 3/2 in the denominator. So x up there and square root of u down there. So this is now the derivative of u by y, partial derivative. Now, x derivative by t is simply 6t, y derivative by t is square root. The derivative is 1 divided by 2 such square roots of that kind times the derivative of the inner function, which will be 2d. We can simplify it a little bit. D squared plus 1, simply cancelling out 2. And now finally, combine all these 4 expressions together. So I'm combining this and writing cotangent. So this will be cotangent x over square root of y times 1 over square root of y times x derivative by t, which is this, 6t, plus u derivative by y. Again, I'm writing a cotangent to make it shorter. Cotangent x over square root of y. Oh, it was minus. All right. I will change it. Minus. This is 1/2. It remains, so this disappears. So it will be minus 1/2 cotangent times x over square root of y cubed times this. Okay, t, and then we have square root of t squared plus 1. This is longish. But, well, that's how it is. So again, you don't have to change anything. You don't have to put t functions instead of x and y, because that will simply make it more complicated and longer. We don't want that for now. Yes?
Why do we put cot instead of cosine?
Cosine divided by sine equals cotangent. I didn't put cotangent instead of cosine. I put cotangent instead of cosine divided by sine.
You can just skip cosine and sine?
Yes, you can. Yes, you can. If you don't know trigonometry. Okay. What I'm trying to show you, I'm trying to show you good habits of writing mathematics. Because the messier you leave the result, the messier the expression is, the easier it is to make mistakes. So normally mathematics involves not only correct calculations and transformations and differentiation and integration, but it also involves writing good mathematics. So whenever you are doing your coursework or bachelor's thesis or master's thesis, whenever, you will need to be able to write good mathematics so that everybody understands. And for that, simplification is important. Writing good mathematics is not only doing correct calculations. It's more. Okay, so this was 1919, so perhaps... Okay, what now? What now? Yes, you can. Okay, I counted you and then more people came.
65.
Okay.
Means почти.
And what does that mean?
Numbers.
Yeah, obviously numbers. Obviously numbers. Obviously
I
numbers.
wonder why you count backwards. That's what it is.
Okay. So now, some exact differentials perhaps, or some of those derivatives, or something. 70? All right. Two variables in terms of two other variables. That's a nice choice. So z equals x squared y minus y squared x, and x equals u cosine v, and y equals u sine v. So we have two variables expressed in terms of two other variables each. Okay, z derivative by x, 2xy minus y squared. Z derivative by y, x squared minus 2xy. So these are simple. I do hope that it's not so terribly difficult to pretend that one of these variables is a constant, because, well, this should be very simple to do. Just keep in mind that when you are deriving by x, y is a constant. I remember that some people had problems last semester when we were starting derivatives, and there were more than just x in one expression. A, what do we do with a? What do we do with pi or e or something, some other vectors? And those are constants, those are constants. Okay, x derivative by u is simply cosine v, x derivative by v, the derivative of cosine minus u sine v. Y derivative by u is simply sine v, y derivative by v is u cosine v. And now all we have to do is simply put everything together. Now you have the parts, and you have to put the parts into that construction. So z first derivative by the partial derivative by u would be derived by x, 2xy minus y squared, multiplied by x derivative by u times cosine v plus z derivative by y multiplied by y derivative by u. Y by u, this one, sine v. Z derivative by v. Again, z by x, 2xy minus y squared, multiplied by x derivative by, it's v this time, so this is this, so minus u sine v plus z derivative by y, again the same, times y derivative by v, which is u cosine v. So, this is it. Again, I want to remind you, don't put x and don't put v and u in here. It's okay to leave the expression using 4 variables. Because if necessary, it will always be possible, there will always be enough time to put u cosine v or u sine v instead of x and y. If you try to do it now, it will serve no purpose at all. It will not help. It will simply make things less pleasant, but it will not be useful. Okay. Some exact, how to write exact differentials. how to write exact differentials. For example, okay, I have a 3-variable function. For 3-variable functions, the procedure is exactly the same. So if I have this u depending on x, y, z is z times e to the power xy, then u derivative by x exponential function will be z y e to the power xy. Why? Because x times y, which pretends to be a constant. So if I derive the exponent, the derivative is y. U derivative by y in a similar way, zx e to the power x, y. And u derivative by z will be simply e to the power x, y, because that will be like a constant. And to write the exact differential, I have to take these and multiply by the corresponding differentials of the independent variables. So it will be z, y e to the power xy times dz plus zx e to the power xy times the, sorry, this was what? This was x. dy plus, and this was u. Oh, I'm sorry, I was going off the tangent. The function is u. And the independent variables, in this case, 3 of them, independent variables x, y, z, and e to the power xy times dz, finally. So the exact differential can be written in exactly the same way for 2-variable functions, 3-variable functions, 4-variable functions, 5-variable functions, and so on and so on. All we have to do is derive by each of these variables and then multiply by the corresponding deltas. The dx or delta x is the same, and put them together in one line, simply like this. So you find the derivatives, which are usually quite simple, and write down the answer. Simply have to write it down. There's not much to do. Okay, from exercise 2, perhaps, well, 2, something from there. Do. About the time, the time. All right. So we will probably need to discuss some of these next time because it's important enough and this is new enough